Hi students, welcome to my lectures on chemical reaction engineering. First of all, I would like to say thank you for making my mechanical unit operations lecture series successful. So with the success, I just wanted to start the new series on chemical reaction engineering. This will be helpful for the both bachelors in science and bachelors in engineering. For the people who want to learn the basics of chemical reaction engineering. I have made the modules in such a way that easy and understand for an average to below average student. Okay. So let us start the lectures. In this entire lecture series, we are going to discuss about the chemical reaction engineering, especially for the homogeneous systems. Later on, maybe in the next lecture series, I might start the heterogeneous systems. So in this entire lecture series, the present lecture series, we will be concentrating on the homogeneous reactions. So let us go into the lecture. So wherever you go, the industry, people want to make a certain product. It could be a distillation. There are a number of unit processes and operations that are existing. One of the unit processes in the industry is which the reaction takes place in a reactor. It is one of the unit process operation, where one molecule is changing in identity to the another molecule. In other words, the reactant changing its identity to a product, the product which may be of the commercial importance to us. So to make this product, okay, we need to use certain equipment, right? The name itself, it is called the reactor. There are number of reactors that are existing in the industry. Okay, like continuous stirrer tank reactor, packed bed reactor, fluidized bed reactor, plug flow reactors. Okay, there are many reactors that are in use. So the basic aim of chemical reaction engineering is to design a reactor. That means finding a specific how much volume of the reactor that is required. Okay, for example, I want 80% product. I have started with some 100 moles of feed, and I wanted to get from this 100 moles, 80 moles will form to the product, 20 moles remains as a feed. That means for a certain conversion, how much the size of the reactor is required, how much the catalyst I have to fill in. So this is called the design of the reactor, and design of the reactor comes with a number of heating and cooling systems, because there are certain reactions which are exothermic in nature. That means from forming the reactant to product, some heat will be released. So somehow we have to remove the heat, otherwise it will build up in the reactor, the reactor will get overheated. For certain reactions which are called endothermic reactions, the endothermic reactions are those from forming from feed to the product, some heat has to be supplied. That means for this reaction to happen, I have to provide some heat to the reactor, because otherwise the conversions will be very low, the rate of reactions will be very low. Okay, the conversion, it's a separate part, mainly to speed up the process of from reactant to product, okay, or feed to product. I need certain supply of energy that is required, I have to supply to the system. These are the things that we have to deal with this. Ultimately, keep it in mind, the crux of the chemical reaction engineering is to design a reactor. Okay, where different heating systems we have to provide, cooling systems we have to provide, all these things comes in the design of chemical reactor, which we will be teaching in the chemical reaction engineering. So let us go in this lecture series, what I am going to teach you. See, the basic aim, design of reactor, it consists of number of aspects. We will be concentrating on few aspects only. Example, for you to design a reactor, you know what kind of reaction that is happening in the reactor. So first of all, you should know what kind of reaction, how fast the reaction is happening. Is this reaction happening in 1 minute or 2 minutes or 3 minutes? That's called, I am talking about the speed of the reaction or rate of the reaction. So that's what you're going to learn in the kinetics aspects. Thermodynamics, okay. I have certain feed which is converting to the product, A gives rise to B. How much amount of A is coming to B, converting to B? that who we are going to decide? That is, what is the maximum possible A that converts to B? Example, 100 moles of A. Is it only 60 moles converting to B and 40 moles of A is remaining as it is, or it is 40 moles of A converting to B, 60 moles of A is remaining at the end of the reaction? That is called the conversion. Who is going to decide? The thermodynamics is going to decide whether it is 40% convection, 50% convection, or 60% convection. Okay? Okay. Let us imagine what kinetics will do. Okay, thermodynamics says only 40% conversion happens. This 40 conversion happens in 1 hour. Whether this 40% conversion happens in 2 hours, whether this 40% conversion happens in 3 hours, who is going to decide? The time is decided by the kinetics. The maximum conversion will be decided by thermodynamics. This is the only basic difference between the kinetics part and thermodynamics part. Okay? Fluid flow. Okay. If it is a certain reaction, if it is a liquid consisting of the solids, okay, what kind of pump we are going to use? And is it appropriate to use centrifugal pump or reciprocating pump, or is it a viscous liquid or non-viscous liquid? Depending upon the kind of feed or the kind of liquid or gaseous system we are dealing with, we have to go for the design of a compressor or a pump. And what is the other aspects of designing a reactor is, what is exothermic reaction? It is heat is getting produced, or endothermic reaction, are we going to supply the heat, and what kind of requirements we have to provide. Okay, jacket consisting of heating or jacket consisting of the cooling, depending upon the kind of reactions and what temperature we have to maintain inside the reactor. Depending upon all the requirements, we have to go for this heat transfers, mass transfer processes. Okay, mass transfer process comes in play whether we are dealing with the packed bed reactor. Okay, what kind of feed arrangements we have to give in a packed bed reactor, because there are some dead zones are there in the reactor. When we pack a solid into the reactor, what happens? Not every part of the reactor will equal reaction happens, because there are dead zones. When the moment the solid packings are there, the more dead zones are going to take place. In such cases, how have to arrange whether I have to multiple inlets and multiple outlets, or single inlet and multiple outlet, these are the arrangements we have to decide that mass transfer process. Okay, basically what are the temperatures, pressures, concentrations that we have to deal with this kind of heat transfer and mass transfer effects. Economics. Okay, that is what we are going to do. Economics means not every time I have to target 80% conversions. Okay, maybe economically I can get 60% conversion, but if I go for 80% conversion, I have to I have to spend more money for that. Okay, whether 60% is more economical or 80% is more economical, that we have to decide, and based on that we have to keep the targets. Okay, not every time we have to reach to the 100%. We have to keep the economics of the process into picture. Okay, what this design of because to design the reactor we have to keep all the things in mind. And what is the size of what is the design of the reactor means? Size of the reactor with specific heating and cooling or material specifications. So what is the size of the reactor? Either we have to calculate what is the volume of the reactor or what is the length, it's about the same, and or how much amount of catalyst I have to put in the reactor. That is what we have to design, right? The crux of the chemical reaction is to design a reactor. So what volume of the reactor, what length of the reactor, how much amount of catalyst I have to put in. So all this for specific conversion, how much I am targeting. For this 80% conversion, what should be the length of the reactor, what should be the volume of the reactor, what should be the catalyst inside the reactor. These are the design aspects we have to look into. Okay. In thermodynamics, that means I have told you that these are the different aspects are there. What is there in thermodynamics? As I told you, thermodynamics decides what is the maximum percentage of reaction conversion it can go, 60%, 70%, 80%. Equilibrium. Okay, thermodynamics says, okay, this is the maximum you can go. You cannot go beyond 80%. So thermodynamics says it's 60%. We have to target for maximum close to 60, right? You cannot, because you cannot go beyond thermodynamics what it is saying. So that's what is the maximum conversions, what is the equilibrium conversions. Or is it an exodermic process, it is an endothermic process, all the things we can get in thermodynamic data. Kinetics, as I told you, thermodynamic decides maximum, okay. To reach this maximum, how much time it requires, whether 1 hour, 2 hour, 3 hour, that is decided by the rate or speed of the reaction. That comes from the kinetics. If it is a first order reaction, a specific speed, 0 order reaction, a constant speed, second order reaction, a different, because order of the reaction decides the speed of the reactions, okay. Next, what is molecularity, order of the reactions, these are the things we are going to discuss, okay. Fluid flow, what kind of pump, what kind of arrangements, heatings, coolings, heat transfer and mass transfer. That means in that heating, cooling systems, pressure, temperature, what is the effect of pressures, what is the effect of temperature. If I keep more pressure in the reactor, am I going to get more conversion or less conversion? If I increase the temperature, am I going to get more conversion or less conversions? Finally, the economics, cost, what is the maximum purity. Beyond that, if we go, I need to put more money into the systems. So that is why we have to deal with the always not just a maximum conversion we have to go, we have to check the economics of the process also. And this is the overall picture where we are going to learn in the lecture series. Finally, we should look into the kinetics aspect. In the kinetics, we have to see how I am going to classify reactions, because kinetics decides the speed, okay. In the kinetics, I should know what are the kind of reactions, because kind of reactions decides the speed of the reactions, okay. That is, we need a classification, how we are going to classify reaction. Am I going to classify the reaction based on speed, or based on order, or based on how many molecules are there in the system, okay. Let us see that in classification of reactions. And we are going to look into the molecularity, how many molecules are reacting in a specific reactions. Order decides the speed of the reactions, temperature effects, and we need to look into the elementary as well as non-elementary, okay. Non-elementary as well as elementary, right. What is the stoichiometry? 1 mole of A plus 2 moles of E gives us to 1 mole of C and 3 moles of D. This is called the stoichiometry part, okay. Ideal reactors, we are going to discuss about plug flow reactor, continuous stirred tank CSTR, continuous stirred tank reactors, packed bed reactors. These are the things we are going to deeper aspects. And multiple reactions in the reactor, okay. A plus B gives rise to C is one reaction, A plus B gives rise to C, D plus E gives rise to F. There are 2 reactions are there. If more than one reaction, we say it as a multiple reactions. So in multiple reaction systems, we defined it as a parallel reactions, that means they go together. Series reactions, that means after one step, second step is going to happen, that's called the series reactions, okay. In that kind of systems, how my rate of the reaction, that is speed of the reaction, is going to alter, because ultimately the speed of the reaction decides the size of the reactor. Somehow if we are able to get the rate, that means how speed the reaction happens. If the speed of the reaction is more, the volume of the reactor will get reduced. If the speed of reaction is less, the volume of the reactor has to more, okay. That is what we are going to. Finally, after the multiple reactions, we are going to see, let us see the temperature and pressures if possible. Basically, in this entire lecture series, we are going to deal with the homogeneous reactions, because heterogeneous is altogether a different lecture series. I will try to concentrate on that. So please be follow. Slowly we will move into the lecture with time. Thank you.